Hello, and welcome to my presentation on DashBot, a deep reinforcement learning system for generating insight-driven dashboards. Let us understand the motivation for introducing DashBot. Visualizations, particularly analytical dashboards, are essential for businesses to understand data. However, creating visualizations can be time-consuming and difficult, oftentimes requiring users to know tools such as Power BI or Tableau. The goal of the authors is to develop a deep reinforcement learning system that can automatically generate insight-driven and visually appealing dashboards for any dataset. As you may have noticed in the title of the paper, the authors use reinforcement learning to solve the problem of creating dashboards. So why reinforcement learning? The intuitive reason for using reinforcement learning is that it is similar to the way that humans explore data and generate visualizations. When humans explore data, they typically start with a general overview of the data and then gradually drill down into more specific areas of interest. They also try out different visualizations to see which ones are the most informative and visually appealing. RL agents also work in a similar way. They start with a state, which represents the current state of the data, and then take an action, which represents a modification to the dashboard. The agent then receives a reward, which indicates how well the dashboard is performing, and then transitions to a new state. Although there was some prior work in the general direction of creating dashboards, they have not been able to address the objectives of insight-driven dashboards. For example, the previous works on visualization recommendation only focused on generating a single chart as opposed to multiple charts in a typical dashboard. There was also prior work on multi-view visualization, which dealt with multiple charts, but they ignored user interactions and were often constrained to select a specific set of attributes in the data. RL for visualization was also explored, but there was no emphasis on generating insight-driven dashboards. Reinforcement learning, on the sound of it, might seem like plug-and-play approach. However, there was still work needed to be done by the authors. Firstly, there are no established RL environments for visualizations. This means that authors needed to develop their own environments. Secondly, the rewards for generating dashboards are non-deterministic. This means that they can vary depending on users' preferences and the specific datasets. The authors needed to meticulously develop reward functions, which we will talk about later. Finally, it is difficult to imitate human behavior when training RL agents to generate dashboards. This is because humans use a variety of factors to decide which visualizations to create, such as their personal preferences, the specific dataset, and the task at hand. Let us now dive into the methods proposed by the authors that address these challenges. The authors propose to formulate the problem of dashboard generation as Markov decision process, also known as MDP. An MDP is a mathematical framework for modeling sequential decision-making under uncertainty. In the context of dashboard generation, the state space of the MDP is a set of all possible dashboards. The action space of the MDP is a set of all possible dashboard modifications, such as adding a new chart, removing a chart, or terminating the exploration. Here is an analogy to help you understand the MDP formulation of the dashboard generation problem. Imagine a robot that is trying to navigate a maze. The robot can move in any of the 4 directions. It receives a reward each time it moves closer to the exit of the maze. The robot's goal is to learn a policy that maps states, which is the robot's current location in the maze, to actions, the direction in which the robot should move. The dashboard generation problem can also be formulated in a similar way. The dashboard is analogous to maze, and the dashboard modifications are analogous to robot's movements. The reward function should encourage the generation of valid, informative, and visually appealing dashboards. This example shows you the exploration episode followed by an agent. The parameters that the agent can adjust include the chart type, chart title, chart access labels, etc. The agents start by exploring the state space at random. As it explores, it learns which actions and parameters lead to the most desirable outcomes. For example, the agent may learn that adding a line chart to a dashboard might be more informative than adding a bar chart. The agent continues to explore the state space until it has found the dashboard that meets its goals. Once it has found a satisfactory dashboard, the agent can recommend it to the user. Let us talk about the reward functions that the authors have designed. The proposed reward function is a multifaceted score that assesses the overall effectiveness of the generated dashboard. The authors mainly designed rewards based on presentation and insights. In the presentation rewards, the authors decided to reward the dashboards which showed different kinds of charts, but not too many, because it puts pressure on the user's cognitive load. The authors also decided to favor dashboards that have just enough number of charts, but again, not too many. The reward function for insights is based on different metrics visualized by the dashboard. For example, correlation, top K, etc. These rewards are combined in a weighted manner to give an overall score. You can see the proposed feature construction for a given state on the left and the model architecture on the right. The dashboard features are first constructed with both column features and chart features. These features are then fed to the LSTM network, which ultimately leads to outputting the action probabilities for selecting the best possible action for the given input state. The RL algorithm used here is called A3C, which stands for Asynchronous Advantage Actor Critic Algorithm. The DashBot's interface consists of table view, topic list, chart editor, canvas view, and recommendation view. The table view shows the underlying data for the dashboard. Users can filter and sort the data to explore different patterns and relationships. The topic list shows the different topics that are covered in the dashboard. Users can select a topic to view the associated visualizations. The chart editor allows users to add, edit, or remove visualizations from the dashboard. Users can also customize the appearances of visualizations, such as the chart type, axis labels, and legend. The canvas view shows the overall layout of the dashboard. Users can drag and drop widgets to rearrange them on the canvas. The recommendation view provides users with suggestions for new visualizations to add to the dashboard. The recommendations are based on users' data and the insights the user has already explored. Overall, these are the main contributions made by the authors. Firstly, the dashboard researchers conducted a study to identify the key design considerations for dashboard recommendations. The authors also developed an RL formulation that takes users' interactions into account so that the dashboard can be updated in real time to provide the users with most relevant information. They also developed a novel deep neural network for reinforcement learning dashboard generation. The deep neural network is able to learn a policy that maps the current dashboard to the next dashboard through modifications. Let's talk about the evaluation methods. The first method of evaluation that the authors used was qualitatively evaluating the generated dashboards using results. As you can see in the two examples here, DashBot generates several metrics such as mean, minimum, maximum, top K features, etc. The generated dashboards also consist of diverse charts. For example, you can see box plots, line charts, bar charts, and scatter plots in these examples. Next, the authors also performed ablation studies to demonstrate the effectiveness of their neural network's architectural choices. As you can see from the study, they identified the significance of different components of the A3C framework, such as invalidity penalty, independent multi-classification. Finally, the authors also gathered user feedback, which is a crucial aspect of evaluating the effectiveness of data visualization tools. The participants were tasked with comparing DashBot and Multivision, which is another model for visualization generation. The participants were asked to rate the dashboards mainly based on 4 key criteria: overall quality, insightfulness, understandability, and aesthetics. The results of the user feedback indicated an overwhelmingly positive response on DashBot. The authors acknowledged few areas as room for improvement. There could be additional types of reward functions, such as chart effectiveness, which can improve the exploration episodes of the agent. The authors also only used Vega dataset, which is fairly simple, but the real-world data differs from Vega and is much more complex. They also acknowledged that there could be more data aggregators for generating insight metrics. Also, DashBot currently only generates static and non-interactive charts. This concludes the presentation, and I thank you for listening.